Hello and welcome to Empowered Learning. This is the fifth video in the Laplace transform video series. And so this video is the one where we actually start to take the Laplace transform of ordinary differential equations. So I'm going to do about 5 examples here so that we can get a feel for how this works. Again, we'll be using the Laplace transform tables that I've mentioned in the earlier videos. For those of you that, just say, hey, I want to jump in and just take the Laplace transform of the equations and not really know all of the intricate details behind the Laplace transform and all that, then this is a video that you want to watch. If you're more interested in knowing, well, why and how does the Laplace transform work, these tables that we get, how do we actually come up with all of that, then videos 1 through 4 in this video series actually goes through all those details. So we're going to start off here and just start by taking the Laplace transform of this first order differential equation. So we'll just do Laplace transform of left side equals Laplace transform of right side. And of course, we know that we can split this up. Say Laplace transform of the first derivative plus 7 times the Laplace transform of our function y is equal to 10 times the Laplace transform of 1. Okay. And so here our goal is to figure out, well, what is the Laplace transform of the first derivative of our function? What's the Laplace transform of our function itself? And what's going to be the Laplace transform of 1. So if we look here at our tables, we'll see that the first derivative of a function, if we take the Laplace transform of it, is just going to be s times whatever the Laplace transform of it is, minus the function evaluated at 0 here. Okay. So we know that for this first part here, this is just going to be s times big Y of s minus y of 0. Okay, so this term here actually comprises of these two terms, times 7 times, by definition, the Laplace transform of y is just big Y of s. And then we say equals to 10 times the Laplace transform of 1. If you remember from our tables here, that was the very first one. The easy one is just 1 over s. So we'll come here and just say that that's 10 times 1 over s. So just 10 over s. Now, at this point, we know that we have an initial condition. And the initial condition is that y of 0 is -3. So we can come in here and say, well, this is just -3. And so in doing that, we now have, I'll just come over here and write it, s y of s plus 3 plus 7 times big Y of s is equal to 10 over s. And so our goal here now is to get all terms with big Y of s on one side, everything else on the other. So I'll have s y of s plus 7 y of s, big Y of s, and that's going to equal to 10 over s minus 3, because this 3 needs to be taken away from this side, so we subtract it from both sides. So from there, if I was to factor out y of s, then of course I'll have s plus 7 left. And then of course I have 10s minus 3 on the right side. And so now if I divide both sides by y of s, then I'll essentially just have 10 over s minus 3, all that over s plus 7. And that ends up being 10 over s times s plus 7 minus 3 over s plus 7. And so this would be the actual Laplace transform of the solution to the function that would actually satisfy this equation. Okay. And so notice that I'm able to write it this way. So since I'm able to write it this way, you'll find out whenever we start to do inverse Laplace transforms that this is actually a pretty good way to leave it. We could combine it together. And if I did that, then of course it would look like this. So both of these terms have a s plus 7. This one's missing an s. So we could just say s here, do it like that. And so now we have 10 minus 3s over s times s plus 7. This is an alternative way you can answer this question. And just kind of depending on the method that you want to use to figure out what y of s is going to eventually look like, we could deal with it this way, or we can deal with it this way to get that particular answer that we need. Meaning, we're basically going to use this and then later on from that figure out what y of t is. But we won't do that in this video. The next one that we'll do, we'll take all these examples and we'll go from the Laplace transform of what the solution is and figure out what the solution is. Okay. All right, let's move on to the next example. So again, for this example, we have another first order differential equation. And we see here that on the right side of it, we have a step function that has been shifted to the right 4 units. So we'll need to make sure that we use the correct Laplace transform for that as well. So again, I'm going to skip some steps here. We know that this will just be the Laplace transform of the first derivative minus 5 times the Laplace transform of the function itself. And then we'll just do the Laplace transform of the step function. And I'm going to rewrite it this way so it's a little bit more plain on what it is that we're doing here. Now, as we said in the first example, we know that the first derivative, the Laplace transform of that is just s times big Y of s minus y, little y of 0 minus 5y of s. And here for that step function, if we look at a chart here, we see that the step function shifted is going to be this e raised to the minus alpha s, all that divided by s, where of course alpha is going to be greater than or equal to 0 in this particular case. So here this will be e raised to the alpha, and of course my alpha here is going to be 4 s, all that divided by s. So e raised to the negative alpha s, all that divided by s. And notice here that our initial condition, y of 0 is equal to 0. So we're going to go ahead and substitute that in. So now this just gives us s y of s minus 5 y of s. So we could factor out y of s out of both terms. And then of course from here, our y of s will just end up being e raised to the 4s divided by s, all that divided by s minus 5, which is just e raised to the 4s divided by s times s minus 5. And this would be our Laplace transform for whatever the solution to this particular equation would be. For our third example, we see now we have a second order differential equation. and particularly a second order linear non-homogeneous equation where the right-hand side of it is one of those functions that we know we could use method of undetermined coefficients for, okay? However, we're not doing that approach here because what we are essentially doing in these problems is we're taking the Laplace transform, well, we're taking an ordinary differential equation and we're using the Laplace transform to essentially turn this calculus problem into an algebra problem, okay? That's one of the main reasons for the Laplace transform. And I mentioned that in the part 1 video. If you did not watch that, if you did, of course, I'm hoping that you recall that. And so that is the reason why we're doing this. We're trying to change calculus-based techniques to solve ordinary differential equation into algebra ones. And we're going to see in some cases, it ends up being relatively easy to do, much easier to come up with a solution than if we would have done it using the differential equation techniques that you're probably studying in your courses. However, sometimes it gets to the point where the algebra just gets insane. And you're going to see some examples of that. So I want you to see it so that you kind of know the pros and cons of using the Laplace transform. Okay. All right. So anyway, so with this example, we're going to say the Laplace transform of the second derivative plus 4 times the Laplace transform of the actual function is equal to Laplace transform of sine of 2t. Okay. Now, for the second derivative, we do a Laplace transform of that. If we look at our chart again, we'll see that the second derivative is s squared, in this case, big Y of s, minus s y of 0 minus y prime of 0. And again, I'm just replacing the f with a y since we're dealing with y's in our problems here. So we have s squared times y of s minus s y of 0 minus y prime of 0. So this first term here creates all 3 of these terms. Laplace transform of y is just going to be y of s. So that's just going to be 4 times y of s. And of course, now for sine of 2t, we're going to go look at our chart again here. And we're going to see that it's going to be omega over s squared plus omega squared. See, sine of omega t is going to be omega over s squared plus omega squared, where our omega in this case for this problem is just going to be 2. Okay. So we're going to have 2 over s squared plus 2 squared. And of course, that'll be 4, and I'll just change that later. So we look here and we see that we have our initial conditions. So y of 0, that's just going to be 3, and y prime of 0, that's just going to be 5. So take that and we say this is s squared big Y of s minus 3s minus 5 plus 4 big Y of s is just equal to 2 divided by s squared plus 4. And of course, from here, our goal is to get all terms with y of s on the same side, everything else on the other side. So we'll have s squared big Y of s plus 4 y of s. And this will be equal to 5 plus 3s, because these need to be added to both sides, plus 2 times s squared over 4. Of course, from here, we could factor out y of s to both sides. And of course, from here, y of s in this case just ends up being 5 plus 3s all over s squared plus 4. and this will be plus 2 times s plus 4 squared here. And so that is what our Laplace transform of this function would be. Again, what some people would like to do is to combine this to be all into one quotient. For right now, we're not going to necessarily worry about that. In the next video, when we actually find what the corresponding y of t is for this Laplace transform, we'll decide whether we want to actually combine it into one quotient or just kind of leave it as is. All right, so for our next example, we'll take the Laplace transform of this equation where we have these two initial conditions. Again, this is a second order linear non-homogeneous equation, and we know that the product of an exponential and a sine function is one of those where if we were trying to solve this by using method of undetermined coefficients to find a particular solution, we could do that. But we want to avoid doing that and basically turn this into an algebra problem. So hence why we're doing Laplace transform. So we're going to take the second derivative of our solution that we'll find out minus first derivative plus 13 times Laplace transform function itself. And then we're going to take the Laplace transform of e raised to the 2t times sine of 3t. So of course, for the second derivative, again, we know this is going to be s squared big Y of s minus s y of 0 minus y prime of 0. For our next term here, be negative 4 times Laplace transform of first derivative, which is just s times big Y of s minus y of 0. And then 13 times just big Y of s. And of course here, notice that we're taking the Laplace transform of a function that we know, but we have this e raised to the 2t in it. And if you remember, this was one of our translation or transformation properties. So switching over to the Laplace transform table here, you'll see that we actually have the Laplace transform of this exact thing here, okay? So this is what it's going to look like. But what I'm going to do is actually use this form of it. And of course, we see that we have that horizontal shift in the s domain. So that's what gives you this s minus a here. And of course, Laplace transform of f of t, which in this case is going to be sine of 3t. If we go back here, Laplace transform of sine of 3t just looks like this. So we can see how this identity works with this identity to give us this identity here, okay? And so here we know that all this is just going to be 3, which is what our omega is. And instead of having just s squared, we'll have s minus 2 squared, because our alpha here is 2. And of course, this will be 3 squared here, which we know that that will be 9. So we have everything set up here. So now we use our initial conditions. So our y of 0 is 4. Y of 0 is 4. And y prime of 0 is 3. And so from here, we just simplify and then collect, try to solve for big Y of S. So again, I'm just distributing everything through here. Okay. And then, of course, once we're here, we'll combine any like terms that we can. And I'm also going to go ahead and group all terms with Y of S together here. So big Y of S is going to be S squared minus 4S plus 13. And then once those three terms are taken care of course, we have this minus 4S here. And then negative 3 plus 16 is a plus 13. And of course, all this would just be 3 divided by S minus 2 quantity squared plus 9. Then from that point, again, we're just trying to solve for Y of S. So we're going to leave all of this here. And on the other side, this will be 3 divided by S minus 2 squared plus 9 plus 4S minus 13. And then finally, we will solve for Y of S. And this will just be 3 divided by S minus 2 quantity squared plus 9. All that times S squared minus 4S plus 13. And then this will be 4S minus 13 over S squared minus 4S plus 13. And so we could leave our Laplace transform in this form here. However, I'm going to switch pages here. If we look at S squared plus 4S minus 4S plus 13 here, if we were to do completing the square on this, then of course we know that whatever this term is here, we take it divided by 2. So negative 4 divided by 2 and square it. That would end up being 4. So we put the 4 here, 4 there. And of course, these first 3 terms here, we could rewrite as just S minus 2 squared. And we see here 13 minus 4 is just 9. So what we're actually seeing is that this S squared minus 4S plus 13 is actually the same thing we've been seeing before, this S minus 2 quantity squared plus 9. So in saying all that, we could take our denominators here and we could rewrite them. Okay. So for this denominator, it could just be S minus 2 quantity squared plus 9. And I did it again. So we got S minus 2 quantity squared plus 9. And of course, for here, since we know that this S squared minus 4S plus 13 is the same thing as what we see here, I can literally just say that that's just going to be the same thing as this squared. So it'll be S minus 2 quantity squared plus 9. Of course, that would be squared. And so we could leave it that way. For our last example, what we want to do here is take this third order linear non-homogeneous ordinary differential equation and find what y of s is for it. So we'll start off with Laplace transform of the third derivative. The pen is dragging a little bit here. Minus 27 times Laplace transform the function that we're trying to find. Laplace transform of e raised to the negative 3t. Now, if we look at our tables here, we'll see that for the Laplace transform for the third derivative of a function, we could use this formula here. And so this will start off, if we use it, since n is going to be 3 in this case, then that would be s cubed y of s. And then, of course, we would have s squared, because n minus 1 or 3 minus 1 is 2, y of 0 minus 3 minus 2 is 1, so that shall be s raised to 1, or just s. And then y prime. And then we'll have one more here. This will be minus y double prime of 0. So we see the s's go down in exponent. And of course, this is literally s raised to the 1 right here, if we wanted to write that. And we could write this as s raised to the 0 if we wanted to, if we actually wanted to write that stuff in. So we see the s's go down in exponent. And of course, our y sub 0, order 0, order 1, order 2. And since this always stops one order less than whatever n is. So go back to our problem here. We see that this first term here is actually going to be s cubed big Y of s minus s squared y of 0 minus s y prime of 0 minus y double prime of 0. Then we say minus 27, and then this is just going to be big Y of s. And so now, if we remember the Laplace transform of e raised to some alpha t, and we'll go to the tables for that, should just be 1 over s minus alpha, whatever that is, okay? And so we see that that's exactly what that is here. And so since our alpha is negative in this case, this is going to turn to 1 over s plus some number. So here this will be 1 over s plus 3 because of that. So from here, we use our initial conditions again. So y of 0 is 2. Y prime of 0 is 3. Y double prime of 0 is 4. And from here, we just write everything in. This is minus, by the way. 2s squared minus 3s minus 4 minus 27 y of s. And that is s 1 over s plus 3. And let's get this looking a little better. All right, so at this point, all terms that have big Y of s in it, we want to get that together. Everything else, we either want to combine terms and or go ahead and get that on the other side. So we'll have big Y of s here, s cubed minus 27. Here we have negative 2s squared minus 3s minus 4. There's nothing else to combine with it, so we're just going to add those terms to both sides. Have the situation here. And then we know that y of s will just be 2s squared plus 3s plus 4. All that over s cubed minus 27 plus 1 over s plus 3 times s cubed minus 27. Okay. And so we could leave our Laplace transform of whatever y is like that. But again, we want to try to consolidate as much as we possibly can. So here what I'm going to do is actually combine it into one quotient so that we can see what's actually going on with it here. So if we look here, I'll give myself some more room. One of the things that we know is that s cubed minus 27 is the same as s cubed minus 3 cubed. So it's a difference of cubes. So we have s minus 3 times s squared plus 3s plus 3 squared, which is 9. Okay. So we know that this s cubed minus 27 here, this is what this is going to factor into. So coming back here, see that our big Y of s this is just going to be s minus 3 times s squared plus 3s plus 9. And here we see this is s plus 3 times s minus 3 times s squared plus 3s plus 9. And so now we're looking at this and we're saying, well, hey, this doesn't look so bad. Okay. We see that this second term actually has more in the denominator than this does. The only thing that this is missing is an s plus 3. So we can combine this and make it all into one big quotient here if we were to just go ahead and multiply numerator and denominator here by s plus 3. Okay, and so that is exactly what we'll go ahead and do here. So we'll just come here and just say s plus 3 here. Do the same thing here, s plus 3 here. And so we'll go ahead and combine everything together. So when we do this, of course, we'll have to multiply this 2s squared plus 3s plus 4. And I'll just go ahead and do that here on the side so that we'll save a little room. So this would be the s times all of these would be 2s cubed plus 3s squared plus 4s. And then if we take 3 and multiply that on through, that would be 6s squared plus 9s and then plus 12. So our result here would be 2s cubed plus 9s squared plus 13s plus 12. And so that is what our numerator would be here, plus the 1. So that would be 2s squared plus, looking at the wrong thing here, be 2s cubed, 2s cubed plus 9s squared plus 13s plus this 12 here plus that 1 will give us 13. Take all of that and that is going to be divided by s minus 3 times s plus 3 times s squared plus 3s plus 9. And you can keep that as one quotient that way. Now, the last thing that I want to do is sort of dive deeper into this. And so just kind of like how we did the last example where we had that irreducible quadratic factor, we did completing the square on it to figure out what that's going to look like. I'm going to do the same thing here, okay? And so I'll do it, and then I'll explain why I kind of want to go ahead and go through the pain of doing that straight up first. So here, if we take s squared plus 3s plus 9 here, oh, sorry, not that one. Yeah, let me make sure. Yeah, that's what I want to do. So s squared plus 3s plus 9. We know that we can rewrite this as s squared plus 3s plus some number plus 9 minus that same number. And again, we're just taking whatever this number here is, dividing it by 2 and squaring it. And that'll end up being 9 over 4 whenever we do that. So if we do that, then here this would turn into s plus 3 over 2 quantity squared for the first 3 terms. And then, of course, this would be plus 9 minus 9 over 4. And, of course, we could simplify this part here. This would be the same as 36 minus 9 over 4, or 27 over 4. And so we'll take situation here and do this as 27 over 4. So we come back here, and we know that we can replace all of this with what we just found. So I'll go ahead and do that here. All right, so we'll put some brackets here. S plus 3 over 2 quantity squared plus 27 over 4. And we could leave it that way. Now, the reason why I'm saying we may want to approach this problem this way by putting it all together in this example is because what we're going to be doing next in the next video is we're going to take all these examples that we've just done, and we're actually going to find out what is going to be the corresponding y of t to go with these Laplace transforms of whatever the solution is. Okay. Now, it's going to turn out that in order for us to get this into a form that's going to be easy for us to use to do what we call the inverse Laplace transform, and simply put here, we're just going to look at our chart, and we're going to say, all right, well, if I see something that looks like this, I'm going to algebraically manipulate it to where I get something that looks exactly like this, so that I can say the inverse Laplace transform of this expression is that. Okay, and same deal here. If I get something that looks along the lines of this, I'm going to say inverse Laplace transform of this is going to be this function here. And so that's kind of where we're going. So in knowing that, I can take a page out of the pre-cal book and do partial fraction expansion here. And if I do that, then of course I know that this Laplace transform big Y of s could be rewritten as some constant divided by s minus 3 plus another constant divided by s plus 3. And then, of course, that divided by, in this case, a linear expression, CS plus D, over all this business here. And of course, we can use partial fraction expansion techniques to be able to figure out what this is and what this is, and what this is. And then from there, once we know what A, B, and C are, and D, then of course we can actually go back to our Laplace transform table. And for instance, if I know what A is, if I go to my Laplace transform table, I know that whatever this number is divided by s minus 3 is going to translate to an exponential function. And so that's how we're actually going to use the tables to be able to perform the inverse Laplace transform. Okay, we're not going to go through the whole thing like how we did in parts 1 through 4 videos, to where we were actually building everything up and talking about properties and all that. We could, but it's just really no need. Okay, so we're just going to use what we have available to us and just algebraically manipulate what we need to get what it is that we need. Okay, and so the next video that I'm going to do will be the last one in this video series, and we're going to look at all these examples and see how did we actually apply these Laplace transform tables to perform the operation of inverse Laplace transform to actually find our solutions.